So I'm going to first mark the center, or try to. So center right about there. And the first arrow I'm going to draw actually is the weight. So there we go, the weight acting downwards. Then I've got the normal force. So to draw the normal force, it occurs at the point of contact, and it must be perpendicular to the point of contact, which means if done correctly, it should go right through the center of the object. Now, the frictional force, I think, is one of those ones where we can have a debate about what direction it should be, but if it's rolling down the ramp, the frictional force should be causing it to accelerate, which means increasing the rate it spins this way. So that would require the frictional force be this way along the ramp. Now, if you rolled something up a ramp, it would be slowing down. The friction would still be this way. Now, I'm not saying there isn't a condition for friction to be in the other direction. If something was attempting to drive itself up the ramp, well, then friction might be the other way. But currently, under the conditions we have, this should be the direction of all three of those forces. Any questions? Now, the first thing I want you to recognize is that we do not get to say goodbye to net force. This is one of the hardest things for me to somehow, rationalize with what I know about physics and what I think about this question. What I mean by that is, hold on, I thought I was writing where you could see it, but I was not. This still has to be true. And since I know it accelerates down the ramp, I know that this must also be true. It has to be. It just seems weird to me because the object isn't sliding, but the frictional force is still acting to oppose motion, and it's still reducing the acceleration. But the way in which it acts is to cause it to turn. This seems hard for me to pull together and rationalize in my head, but it has to be true. Newton's law is a law, and I can't just, assume it doesn't work because it's not convenient to me. So even though it's not sliding, the frictional force is still reducing its ability to accelerate. The reason why, though, shouldn't surprise you. The object has rotational inertia. The frictional force is being used to spin it, but that inertia is preventing it from having a linear acceleration. That's why it's right there. That's why it shows up there like you would expect. But we also still have normal force equals mg cosine theta. There's no difference there. We still have a normal force. And it's still based on that angle. In fact, we can go one step further and remind ourselves that friction has to be equal to u times the normal force. But again, it's an inequality. So I really don't know how much friction there is. I just know it has to be less than or equal to mu times the normal force, which is why I can't use forces to figure out what I want to figure out. I have to use torque. Now, here's where things are going to get a little bit weird. For me to evaluate this using torque, I need to identify the pivot point here. And most people, I think, would like the pivot point to be here. Makes a lot of sense. The problem is that that's not the pivot point. It moves. It's moving about that point. The actual pivot point is here. It pivots about this point. The problem is that it only pivots about it instantaneously until it's touching the next point, and then that becomes the pivot point. In both cases, the pivot point is moving. But instantaneously, this point is not moving, and the entire thing is pivoting about it. Now, I can't explain this to you today why this is true, but this is the actual pivot point. But you can still do the problem if you choose the pivot point to be the center. I'm going to call that a virtual pivot point. These are not words that are in your book. I'm making them up on the spot. But what I would like you to do is I would like you to do the net torque equation. You know that it has to equal I alpha. And I want you to choose whether you're going to do it for the actual pivot or the virtual pivot. Now, let me finish before you have your hand up. There's two things you're going to do differently today. First, and I'm doing this on purpose, and I have a reason, I promise. I don't want you to assume it's a disk. I want you to use moment of inertia of I, which means I have to add to it that it has a radius of curvature of R. This is important because if you're going to use the actual pivot point, you will have to use the parallel axis theorem for the moment of inertia. But if you're going to use the virtual one, well, you're just going to use I. But I would like you to make sure that you go at least one step out from here, and that is to put it in terms of the linear acceleration. Okay, James, what was your question?
My question was, are we going to use the parallel axis theorem? Like, yes.
I sometimes have the answer to your question in mind. So, all right, folks, I want you to do this. You don't need me to do this. It's not particularly tough. Pick one and go. Just pick one and go. Feeling extra frisky? Pick them both. I don't really care. But take a look because I'm about to dim the screen for a minute. Ready? I'm going to dim it so that you have a picture, right? And you have all the stuff you need? Jackson, you good? Well, here's what I got. And you should compare it to yours and see if you got the same thing. Whether you did the virtual or the actual, yours should appear here. Now, I might have rearranged it a little differently than you, but I tried to arrange it so that the I and the R was together. We talked about that a little bit before, but moment of inertia for round objects tends to have R squared in it. So it seems like getting the R squared together isn't a bad idea. Now, the problem with the virtual one is that I can't use the virtual one to figure out anything. Not on its own. It can't tell me the frictional force because the frictional force is in terms of the acceleration. They can't tell me the acceleration because it'll also be in terms of the frictional force. But the actual one, I can actually solve it right now for the acceleration and get an expression for the acceleration. So before I go on, does everybody understand how we got the torques for each? That for the weight, the torque was R, the torque arm length, times the force, mg, times the sine of theta, because this has to be theta. The normal force doesn't apply a torque in either case, because the normal force for the virtual pivot is at an angle that is 0 degrees. And it's also got a torque arm length of 0 for the actual pivot. So that's why it doesn't appear in either. The frictional force doesn't appear in the actual equation because it's got a torque arm length of 0. And mg sine theta doesn't appear in the virtual one because it's got a torque arm length of 0. So each one only has a single force causing a torque. But like I said, the actual one lets me come up with a relationship for the acceleration, which I'm going to write in a way that appeals to me, even if it doesn't appeal to you. I like writing it like this because all of that has to be unitless. But my answer has to be in meters per second squared. So G carries all the units. So everything out of parentheses has to be without units. Now, there's nothing particularly interesting there, but I like the fact that it's got the mass in all three terms. No matter what the moment of inertia of this object is, it's going to have the mass involved. Ultimately, I hope you kind of see that whatever this is going to be, this I over R squared. So, I mean, consider that off to the side, I've got it written here. This I over R squared has got to be a fraction with the mass in it, right? If you look at all the things that can roll, it's mr squared for a ring, 1/2 mr squared for a disk, 2/5 mr squared for a solid sphere, 2/3 mr squared for a empty ball. Whatever I put in there for I, I'm going to get a fraction and m, which means m's in every term. It also tells me that whatever is going on here, it's less than 1. Has to be. Has to be less than 1. So it's going to have an acceleration less than g. None of that's a surprise. But also it's got to have an acceleration less than g sine theta, which is something that would slide down that ramp. So that has to be true. No matter what it is that rolls down that ramp, it's going to be rolling slower than something that would slide without friction. Period. Now, I'd like to go one step further here, and that is I would like to have an expression for the frictional force. That's not too hard to do either because I can do that right here. Do you guys see that okay? So I'm a little out of space. So let's see if I can't give me a little bit more space here. So when I substitute, this is going to make for something a little bit odd, and bear with me. We've seen something like this before, but it's been a long time. I have IR squared times m in the numerator, and IR squared plus m in the denominator. That looks pretty ugly. Do you mind if I just multiply top and bottom by r squared? Because if I do, it might make it look nicer. You might want to rewrite it, but I'm not going to do that. This appeals to me quite a bit. First, do you realize that the denominator is the parallel axis theorem? And the top is just the products of the moment of inertia and the mass. It's no longer unitless. Everything in there has to work out to kilograms, which doesn't surprise me because it's a force. So it should be kilograms meters per second squared. But I do like that in this case, the amount of friction is dependent on the moment of inertia. Meaning if I have the same ramp and I put a ring or a disc on it, they don't experience the same amount of friction. Now, it's not clear here, but what would experience more friction? A ring or a disc? You're not going to be able to see it really easy here. You could figure it out. It's whatever would work out there if you put it into numbers. But can you rationalize why one would have more friction than the other? Same normal force. Which one's harder to turn? Probably going to take more friction. It probably pulls more friction from the system to get it to turn. If you don't believe me, compare them. Put in mr squared and compare it to 1/2 mr squared and see what you get. But if I put in mr squared, I'm going to get a bigger number on the top and a slightly bigger number on the bottom. Put in 1/2, I get a half of the number on the top and a slightly smaller number on the bottom. Pretty sure I'm going to get more friction with the ring than the disc. But don't take my word for it. I think we can actually figure something out from this. Now I want to stop right here because this is a point in 7th period where I usually become a little bit frustrated with body language. How many of you have any questions leading up to this moment? This is a lot of work. There's a lot going on here, and it is alphabet soup, but I want to make sure our questions are answered. Yes, Matt.
My logic when I was thinking about which one has the most friction acting on it is that if you release both the ring and the disc, and they're the same mass, the disc would be spinning faster, right?
Okay.
At the same time, and thus the work that is done on it, that putting the energy into rotational kinetic energy would be greater. So I thought friction might be greater on the disc.
Okay, so just so you guys at home, I don't think you could hear Matt at all, but Matt was indicating that he thought his rationalization for the friction being less on the disc was because the disc would be faster, the friction would do less work on it on the way down, and therefore it would retain more of its translational kinetic energy. And that's an excellent reason to think of it too. Also, you could have just said that the disc is going to have a greater acceleration than the ring. They both have the same mass, so the ring must have more friction too. You can look at it right from the acceleration too, which we had. We put the ring and the disc on the table. Which one made it down first? The ring or the disc? Let's make sure everybody's paying attention. When I put the ring and the disc at the top of the ramp, which one made it to the bottom first? Wow.
Disc.
Hold on. I don't want this to be recorded. I want you to take this with us to another page. We need space to work. So I know you've got it just written in front of you, but I have to, memorize it, go over to another page and rewrite it all, which is part of the reason why I was careful to write it in a way that I could remember. We have an expression for the frictional force that has everything to do with the system and nothing to do with friction. Right? This is all about masses and shapes and the angle of the ramp and G. But I also know that the frictional force is related to mu times the normal force. I know that to be true. Moreover, I know that the normal force is related to the angle and the mass. It seems to me that we could come up with the true condition for rolling. We can determine the threshold. I mean, we can tell if the shape we have and the angle we have and the amount of friction we have will allow our system to roll for any system. And you might think that what's the point of that? Well, I'll tell you, it's exactly the point. If your robot is supposed to look for the people who are trapped under the building and they have to go down some kind of steep slope, do you know if it's going to make it without sliding or not? That's probably something you would want to know. You would want to design it in such a way that it would have the maximum potential not to slide. How would you do that? You'd have to understand the conditions when it would slide. These are the conditions. I can put all of these conditions together. It might not be clear why I'm saying it to you guys, and I'm a little frustrated. So let me at least get you guys started. That has to be less than or equal to mu mg cosine theta. This is the condition. These conditions have to be met and balanced. Clean it up. Give me one trig function. Cancel out the stuff that can be canceled. You can do math. Don't wait for me to do it now. Clearly, I've done enough. You don't have to worry about checking the time. I got it right here in front of me. You got 15 minutes. More than enough time. Now you got to hit that door the moment the bell rings, but it'll be all right. Now, I think a lot of people make it to about here, but I don't want to stop here. First, I'm not real good with cotangent. Are you? I just know tangent better than cotangent. Not that that matters too much. What I really want you to think about is over here. If I flip this fraction, then I can get a 1 plus a number. But like this, I can't. So I want to invert both sides. If I invert both sides, I get I plus mr squared over I. And this side, I just get tangent over mu. That's what happens when I flip both sides. But I've come to understand that students don't understand that you can flip both sides of an equation. Would you like me to do it in a different way, like multiplying both sides of it by the reciprocal? Are you sure? Because what you have to also understand is that you have to flip your inequality if you invert both sides of an equation. And 4th and 6th period didn't know that. Does 7th period know this? Now, that allows me to do something on the left side here that I think has value. This is it. These are the conditions. It rolls under these conditions only. Now there's 3 conditions, right? Coefficient of friction is a condition. And the angle of your ramp is a condition. And the shape you choose is a condition. These are all conditions of your system. But this might be a little odd to you, but I think it's neat. The left side is unitless. It has to be because the right side is unitless. Mu has no units, and none of the trig functions have units when they're done. So this is a unitless equation, and it's all a condition. Yes, sir?
Wouldn't it be mr squared over I?
Thank you. Sorry. You're right. Even better. Now, I is going to be something that has mr squared in it. You do realize that, right? At worst, it's mr squared because it's a ring. At best, it's 2/5 mr squared because it's a solid sphere. But that's important to understand that no matter what, this number can't be smaller than 1. If you look at all of the versions of moments of inertia that we have, the biggest it can be in the denominator is mr squared. Everything else is a smaller number, which makes this number 1 or greater every time. You guys see that? Now, that being said, that suggests something, that the smallest the left can be is 2. But that's on the greater than side. Right? That's the smallest it can be. Other stuff will be easier to turn, but the hardest thing to turn would be a ring. And what's the highest this can be? Yep, 1. Coefficient of frictions can't be greater than 1 unless you're gluing the surfaces together. I think you can tell me what's the greatest angle you could possibly have and still maybe have some friction. Let's put a ring in there. Put a ring in there, this becomes 2. Stickiest surface, 1. You're going to get an angle, a specific angle. You can't go up this wall. Got it yet? I know somebody's got it. Everybody doesn't have to drop onto their calculators. 63 degrees. That's right. That's pretty steep, so you know. But still, we got an angle out of this. Now that's for a ring. Rings are hard to turn. Yeah, if you had a disc, maybe. But I'll tell you this, every bicycle tire is a ring. Right? Every one of them. There's nobody on a bicycle going up a ramp 63 degrees. They're sliding back down. Or worse, they are cartwheeling back down because their center of mass is probably not at the middle of the ring. Yep.
Wait, then how does that explode? I mean, I don't know, but like, you should have seen those like, trucks with big tires go up like this really steep cliff.
Have you ever watched them go up the really steep cliffs?
Yeah.
Then you know two things about them. A, they got a running start, right? And B, look at their tires. Okay. We're not dealing with just friction anymore. We're dealing with something that is grabbing onto the road. And that's a little different. On the other hand, you should ask me the question about roller coasters. They're consistently greater than 63 degrees. How does that work? Well, they clamp the wheels onto the bars, right? They ramp up the normal force in an artificial manner to create more friction so they will continue to roll. So those are things that they do purposely because we have these conditions in place. You can't get around these conditions. Now, I think this is kind of neat. I think this problem really ended over here, but I like this idea because although this doesn't show up like on the AP exam that often, this is that part F on that one FRQ that asks that ridiculous question at the end. Yeah, you can still get a 5 without getting this one right, but this is that kid who's going to get every available point. They're going to make it all the way up to here, and they're not going to waver. They're going to know there's a condition. What does that mean? What can I boil away from this to get down to the absolute part of the condition? That's it right there. That is that absolute part of the condition. That might not be you, but it could be. All right, I like this question. It had a lot of neat stuff in it to me. I hope you're able to follow along to here. But I want to talk about one more thing now that I have 7 minutes left. And I want to do something that I think is in the same vein, but completely different. So one more thing. You have time for it? Or do you have a place to be? Because I want to talk about a governor. Anybody ever heard what a governor is? Or a governed system? If you ever rented a U-Haul, then you probably know what a governor is. And what I mean by that is they govern their engine so they can't go past a certain speed. Most all of them do it electronically now, which means that they know when the thing's going 55 miles an hour and they just don't let you go any faster than that. In the old days, they used to put a block underneath the gas pedal, which, you know, that lasted about 5 minutes after I left the place and just pulled the block out, did what I had to do, then put the block back. Nowadays, they govern their systems a little bit different. They electronically govern them, but there are mechanical governs. This is a mechanical govern. I'm going to try and get away with some of the stuff that's here. I didn't want to spend the time to draw it all. You've seen these before because they're in science fiction movies where they're showing all the sciencey stuff and there's two things spinning somewhere, or on railroad movies where they show the big steam engine. They'll have something like this where you'll have two weights that are hung by a rod and they spin. And when they spin, they can lift up and down. You guys know what I'm talking about? These are a mechanical governor. Generally on a steam engine, a mechanical governor like this governs how fast the steam can escape the engine to be applied to the piston. It is harder for steam to escape the engine the faster these spin, making it more difficult for the engine to increase speed after it reaches a certain point. Mechanical governors work in a way that when the system reaches a certain speed, it gets harder for it to go faster. It's a mechanical governor. So a mechanical governor of this state has a mass that's hung on a light rod, and it's hung at an angle away from the center pole. And let me just ask you a quick question. How many of you recognize that as you spin this, the balls are going to spread out further away from the center? Okay, great. So could you do me a real quick favor and find the moment of inertia of this system? You can treat the balls as point masses and the rods as a very little inertia compared to the balls, meaning you can ignore the rod's mass. So just come up with a moment of inertia of the system. Now this shouldn't be too rough. 2 point masses, a distance, whatever that is, away from the axis of rotation. And does that clue you into as to what to do? I think I'm gonna have the number 2 here. What else am I gonna have here? M, yeah, M's gonna be next. And what else? L, yep, L is gonna be there. What else? Sine theta. This is the moment of inertia of this object. This object's moment of inertia changes. The faster I spin it, the harder it is to spin. Right? Because the faster I spin it, the more the ball's gonna spread out. Go ahead.
Why isn't the L sine theta squared?
It is. You don't see it there? Let me draw it a little darker for you just to make sure you see it. Now here's the harder part. And we have 3 minutes, so maybe you can do it, maybe you can't. Can you figure out a relationship between the rotational speed and the angle? There's got to be one. We just said that the faster you spin it, the bigger the angle is. I'm thinking this is probably a centripetal motion kind of problem, where the net force has to equal MAC. You can probably focus on just one ball for that, by the way. Take a big risk saying in class that you're going to focus on one ball, but I did. Hope you appreciate that risk, especially, you know, my tables, I giggle a lot. Yeah. If magnetic dipole moment makes you giggle, and I say focus on a ball, that doesn't make you giggle. What is wrong with you people? I believe in you guys, but I want to see if you can get to this point, because there's something I want to talk about when we get there, and it's taking way more time than I want to take. Oh, 2 minutes. You guys with me? We've done this problem before. Net force in the Y, net force in the X. I won't be able to make my point if we don't hurry. Is this what you guys are doing? I mean, I'm done. I got one more thing to do here, and I get omega in terms of the angle. You see that the sine theta is canceled though, right? Because tangent is sine over cosine. I got a sine on both sides. So I've got a omega squared equals G over L cos theta. Now, I have to let you go, it's fine. But as the balls lift upwards, you do realize that they gain gravitational potential energy, which only occurs as their kinetic energy increases. It's an interesting idea, isn't it? It takes more energy to spin them the faster they spin. We should be able to figure out how much energy they're sucking from the system when they spin. But okay, goodbye. I had fun doing this one, maybe a little bit.